Hello everybody and welcome to our interim presentation. We are Team 6, Darren Alev, Shanoli Kumar, Akshat Mantri, Louis Taiman, and Ijo Tien, and the product we will be covering today is an air sanding disc dispenser.
Our product is designed to align the vacuum holes of a sanding disc with the corresponding holes on a sanding machine so that during operation, the sanded chips can be vacuumed away from the operation zone by the machine. 3 alignment rods line up the holes of the sanding discs. The circular base of the sanding machine is pushed up against the blue guard, and the holes on the machine are inserted on top of the rods. The machine is pressed down and the sanding discs are attached to the machine with Velcro. As the sanding machine is lifted, with its disc reloaded, the extension springs around the rods lift the rods back up into their original positions. Spare discs can also be stored inside the yellow housing. This product was specifically designed to reload the machines used to sand down engine blocks and car exteriors on a production line manufacturing 63 cars an hour. The estimated production volume for our primary and secondary customers is 5,000 units per year. And here you can see an exploded view of the product. Each part is clearly distinguishable, including the bushings and the extension springs that aid the travel of the alignment rods. The assembly has 16 parts in total, discluding the fasteners, with 10 of them being unique.
The goal of our product is to dispense a disc. This is first done by loading discs down below into the spare disc tray. Secondly, active discs are loaded into the top of the tray, and this is completed by aligning disc holes and then consecutively stacking the discs on top of each other with their holes aligned. The next step in the process is to release the active disc from its position, and this is completed by positioning the sander into the indicated location on the mechanism where the crescent will engage it, and the sander holes will line up with the disc holes. The sander is then lowered to touch the disc, and the Velcro engages from the sander to the disc. The next step in the process is to reset the mechanism, which is done by lifting the sander from its resting position, allowing the rods to raise, sending a new disc into the active position. To assure dependability, this is completed by engaging the Velcro from the active disc to the sander. And in order to enhance the product, this design will decrease sanding defects, increase total disc storage, saving time, and eliminate dangerous rough edges that could be occurring on the manufacturing floor.
So after the functional analysis, I wanted to talk about the primary and secondary customers of our product. The primary customers of the product will be manufacturing plants in the automotive industry or similar factories working on manufacturing and assembly of large metal products. The reloader itself will ensure alignment of vacuum holes on the discs and the machines and will significantly reduce the reloading time. This will allow the operators to keep up to the pace of production and improve the quality of sanding. The anticipated volume per year will be around 4,200 units per year for our primary customers. The secondary customers of the product would be individuals using the reloader for personal use. This can be either recreational users or woodworkers. And the product will be used to improve the quality of the air sanding processes, and the anticipated volume per year will be around 800 units per year for our secondary users.
On this slide you can see our fishbone assembly sequence diagrams. On the left is sequence 1, where the stand is initially attached to the base plate, followed by the guards, and then the bushings, alignment rods, and springs leading to the complete assembly. On the right is sequence 2, where the bushings, alignment rods, and springs are placed on the base plate first, followed by the guards, and then the stand leading to the complete assembly.
After looking at the assembly sequence analysis, we can begin to compare the 2 fishbone sequences. Our comparison criterion scale ranges from 1 to 3, with 1 being the worst and 3 the best. Using our 5 standard criterion, which include transferring and handling, locating parts, fastening and joining, testing subassemblies, and assembling in parallel, Sequence 1 had a much lower total score compared to Sequence 2. This indicates that Sequence 2 is better to use in future assemblies.
This slide presents our function component mapping matrix. Each row represents one of the 10 parts in our assembly, and each column represents one of the final functives of each branch of our FAST diagram. As you can see, each part has at least one associated functive, and each functive has at least one associated part.
To talk more about the bill of materials and a rough cost estimation for our mechanism consists of 10 unique parts and a variety of different manufacturing processes such as CNC machining, 3D printing, lathing, and milling. In its current state, the guard of the part is 3D printed. However, for mass production, we plan on using injection molding instead of the current 3D printing method.
Our product family design comparison highlights which functional analysis components are consistent among customers. Our chart indicates that differences among customer groups are between the aesthetic of the design and quantity of spare disks stored. The function component mapping matrix and bill of materials shown previously indicate that these differences occur in the stand and guard parts, both of which lie in the middle range when looking at the total cost in each part. Finally, a big thank you to everyone who listened to our presentation.